Okay, so the last thing from 2.4 is more doing applications, but these are going to be very special type of applications. These are applications involving what's called direct variation, and they're very simple linear equations. All right, so whenever we have two quantities, say x and y, um, are directly proportional to one another. Right, so they're directly proportional. So y varies directly with x. So there is a single correlation between x and y. When x does something, it forces y to do something, and it's the same something every time. So again, as long as that k is not 0. So what we do is we call that variation, that proportion between them, k. Right? K is the variation variable. And so what we say is y is equal to k times x. Right? K is again called the constant of proportionality, or the constant variation. So it's the same relationship between every x and y value. Alright, so the relationship between x and y in this case is linear. It's a very simple line that actually goes through the origin. Alright, so the graph of that, and for some reason that's really small, but the graph of the y equals k times x, and k is the slope. Right? The slope of the line passes through the origin. The x and y intercepts are 0, 0. Right? If we know that a pair of values have direct variation, we can easily find that slope, that constant. Right? Once k is known, then the equation is just y equals whatever k times x is, and then we can use it to determine other things. And there are a lot of applications where this happens. Right? We're going to look at a biological example in a second, and then we're going to look at a common physics example that actually you would do if you went on to take calculus. And then a few other examples of applications at the end. Alright, so a simple example of a direct variation would be, we know that light travels faster than sound. Right? And so in a thunderstorm, thunder and lightning happen at the exact same time. But we see the light before we see the sound. And because there is a direct relationship between the distance the sound has to travel, the distance the light has. So there's a direct correlation between when you're going to hear the thunder and how far away the storm is. All right, there's a direct correlation between the time it takes you to hear the thunder after you see the lightning. That'll give you how far the distance is from the storm. We usually say the center of the storm. All right, so the model is that model. The distance the storm is from the center is the direct relationship is 1080 times t. Alright, where time is in seconds. Alright, and that's the seconds it takes after you see the lightning to hear the thunder. And d is how far away then the center of the storm would be from your location. Right? And it's directly correlated, so the time tells me the distance. That's the correlation. The k that does it is the 10,000. Right? So, example, so there's the direct variation equation. And so if you're watching it, you see lightning, and you count 10 seconds later, you hear the thunder. If it takes 10 seconds to hear the thunder, then we plug it into that equation, so it'd be t times that value. The center of the storm is 10,800 feet away, because of how the sound travels and how they're correlated. If I see lightning and it takes 30 seconds to hear the thunder, alright, well then the distance the storm is further, right? It is 3,240 feet away in that case. And so that's the linear equation for the direct correlation between the time it takes to hear the thunder and the distance away the storm is, right? And there's a direct relationship between that. That's what there's a direct relationship, and we know the relationship is that number 1080. Alright, so what this illustrates is the distance the storm's center is a constant, that's why it's a linear case. It's a constant multiple of how long it takes to hear the thunder. When time is doubled, the distance is doubled. When the time is tripled, the distance is tripled, and so on. Alright, because there's a direct correlation. Alright, the distance always varies directly with time, and it's the same variance. It's this equation. Alright, so this is a simple example of direct variation, and then we're just going to look at some other examples. Right, another example, so like I said, we're going to do one in physics. If you ever taken a physics class, you would have done Hooke's Law in high school. If not, if you take a physics class in college, or even if you go into calculus, this is a law that they cover in both of those classes. And so Hooke's Law is an example of direct variation. So what it says is we've got springs, and springs, how hard it is to pull a spring out or compress a spring is directly related to, how strong the spring is, how dense the material is, and all of that is. And so there's a direct correlation, direct variation between the amount of weight that you can hang on a spring and how far it stretches the spring, right? The more weight you put on it, the further that string's going to stretch out. And so this law is called Hooke's law, right? So that's what it is. So with no weight, the spring's just hanging there. We add a force to it, we add a weight to it, and how much weight we apply here will directly correlate to how much that spring will stretch. And it should make sense. The more weight I put on, the further it will stretch out. And so if I double it, it'll double the distance it pulls the string. So there's a direct correlation. If I triple the weight, it'll triple the distance it stretches the spring. All right, so this, what's called Hooke's law, is a law of the direct variation. All right, so the constant of proportionality, that K value, is the spring constant. All right, and it's related to the force applied to stretch the spring a distance of x beyond its natural length. So that's what I mean. This is its natural position. This would be the distance it's been stretched by. What caused that stretching is this force. And so it is that simple equation. All right, force, the weight, is directly proportional to the distance the spring is stretched, right? So the force, which again is my weight, is directly proportional to the stretch of the spring. Right? The more weight, the further it will stretch. And then that K constant, that has to do with also, every spring is different, right? And so every spring could have a different K, because if it's like the trampoline springs are pretty tight, right? It takes a lot of force to stretch those. And so those would stretch differently than, say, a slinky technically is a spring. It doesn't take a lot of force to stretch that out. All right? And so that K is involved in, again, figuring out, well, how hard it is, how much weight do I need in order to stretch it out. Right? That's what that K finds out. And so we're just going to do some simple examples. So suppose a 12-pound weight is hung on the spring, and it stretches it 2 inches. So again, this force up here would be 12 pounds. This X would be 2 inches. That's what it would be. So it's taking 12 pounds to pull that spring down 2 inches. Find the spring constant. Well, that's the K value. Find the K value and then use it. So I'm going to use my equation to figure out, well, what if I put on 19 pounds? How far will it stretch it? Well, just knowing that it stretched 2 when I did 12 pounds, I know it should be at least beyond 2 inches. All right, but we'll do A first. So when we have a weight, so that's the force, it's directly proportional to the constant times the X value where it's stretched. And so we have a force of 12 pounds, stretches it a distance of 2 inches. All right, find K. We'll just plug those in. So 12 pounds is my force, K is what I'm looking for, my X is 2, and then it's just simple solve. So my K, my spring constant, is 6. And then we'll use it. Well, now we know the force equation for this particular spring. The force is equal to 6 times the distance it travels. And so now we're going to use the force equation here to figure out, well, how far will the spring stretch if we put a 19-pound weight on it? All right, so I'm going to put a force of 19 pounds. What's the X value? All right, so 19 goes in the force spot, so make sure you put it in the right spot. I'm looking for the X spot. So I'm solving for X, so I divide out by my 6. So it's 19 divided by 6, so it would be exactly 19 over 6 inches. Or if you found the decimal approximate, 3.167 inches. All right, so it makes sense it should be further, right? I put more weight on it, so it should stretch further than 2 inches. It actually stretches a little more than another inch, right? It stretches to 3.167. And so that's an example of Hooke's law. All right, so we're just going to do a few more problems just knowing it's directly proportional. All Alright, so this is just a couple of generic examples, and the book does do a few of these, and you'll have a few of these on your homework. And so this is how you solve these when it says y varies directly with x. And we know y is equal to 12, x is equal to 8, find k. Well, y varies directly is implying this equation, that y equals some constant times x. You've got to remember that. So if the problem states something varies directly with something, that varying is there's a constant there. And then we find k by using the p. They have to give us some information in order to find k. Well, we find k by plugging the information in. I know y is 12, x is 8. Plug it in to find my k. So 12 equals k times 8. Solve for k. So it comes out 12 divided by 8, which is 3 halves or 1 1/2. So you can do it either way. So 3 halves or 1.5 is the k. Alright, then write the equation. So y is 1.5 times x is the exact variation equation. So there's the variation with the known k. And then we usually ask you to use it. Alright, so there's the variation equation. And then see what's y when x equals 18. Alright, so y equals 1 1/2 times 18. So y is 27, or sorry. Yeah, 27, that's right. I thought I plugged in 15 times 18. Alright, 27 when you take 1 1/2 times 18. Alright, and there's, again, we'll do another simple example. I actually think this one I did take directly from the book. Alright, t varies directly with x. Suppose t is 33 when x is 5. Find t when x is 31. And so this one is very simple, but there's the line that's important. T varies directly with x. So that means t equals some constant times x. That's what varies directly with. And they didn't come out and ask you what k is, but I have to find k in order to find this equation. Alright, so that's where I use the information. I know t equals 33. If x equals 5, we'll plug that in. 33 equals k times 5, divide by my 5, and so k is exactly 33 over 5. So it's up to you. I would probably just leave that exact. You could change it if you wanted to 6.6 if you prefer. 33 over 5 does simplify to 6 over 6. Alright, so there's k. And so my equation is t equals 33 over 5 times x, and then they ask you to use it. What's t when x is 31? Alright, so I'm going to erase this to do that work. So I want to find t when x is 31, and so it's just plug that into this equation. So t equals 33 over 5 times 31, and so t is, whatever that comes out to be, 204.6 is what my t value is. Alright, so what you have to remember is when it uses this term, it means that equation. T directly is vary with x, means t equals x times some constant. Now we're going to do another spring example, Hooke's law again. Alright, suppose an 80-pound force is used, so this time we're putting the force on top of the spring. Alright, so we're compressing it, but it works the same way. There's still a direct variation whether you're pushing the spring down, compressing it, or stretching the spring out. It works exactly the same. Alright, so we have an 80-pound force compresses a spring by 4 inches. The force equation, what's the force equation, and how much force would be needed to compress the spring? Alright, so what you have to remember about Hooke's law, it is the direct variation. The force directly varies with the change in the spring. So k times x, was x is the distance the spring is compressed. And so in this case, they told me a force of 80 pounds can compress the spring by 4 inches. So I know a force of 80, and the spring moves by 4 inches, and plug it in to find k. So 80 equals k times 4, divide by 4, and so k equals 20. And so my equation for my spring is force equals 20 times the distance it's compressed. Alright, and so there's what I need. I needed to do all this in order to answer the question. So there's the equation that I'm now going to use to answer the question. How much force will I need to compress the spring now by 7 inches? So I'm looking for the force when x is 7 inches. So I plug 7 in. So force equals 20 times 7. And so it takes a force of 140 pounds to compress it by 7 inches. It takes a lot of force. It'd be a pretty heavy weight you'd have to put on that spring to compress it by 7. So again, it would push it down and make it 7 inches smaller than what it normally is. Alright, next example. Alright, so I believe this might be the last example. The maximum lay. Alright, maximum lay, which means that you have a horizontal beam. Right, you have, whatever it is made out of steel or something, some type of beam, can carry weight that's directly proportional to its width. I actually think I mistyped that. That should be load. There we go, that makes more sense. So the maximum load would be how much you're carrying, right? If you're carrying, a heavy book, that's your load. All right, so the maximum load that a horizontal beam, so again, it would be a beam, it would either be a big, strong piece of wood beam or a steel beam or some type of beam, can carry weight directly, so proportional to it. So the wider it is, the more weight it can carry, all right? And it's proportional, right? The wider the beam is, the more that it can carry, the more load it can bear. Alright, so suppose we have a beam that when it's 1.5 inches wide, it can support a load of 3,300 pounds. Right? If the board is 3.5 inches wide, how much more load could it support, or how much load could it support in that case? And so again, there's the directly proportional, which tells me it's our special case. Alright, so I'm going to let the load be the y value, the width be the x value, because the load is directly proportional to the width, and so it'd be the equation y equals some constant times x. So if you can read that, that's the load, the weight. So y equals the load in pounds, x equals the width in inches, and then they give us one. So if a beam is 1.5 inches wide, it can carry a load of 300 pounds. And then we'll have to find the equation in order to answer the question, right? So I need to figure out the equation so I can plug our 3.5 inches into it. So I just plug my y in, plug my x in. So y is 300, k is what I'm looking for, x is 1.5. Divide by my 1.5. And so the constant in this case would be 200. And so my equation is 200 times x. And now this is the equation I need to answer my question. So if the board was a little bigger, if it was 2 inches wider, so 3.5 inches wide, how much could it support in that case? So now to answer the question, when x equals 3.5 inches, what's the load? What's y? And so I just plug it in. 700 pounds. Alright, so if it goes, so again, that's pretty significant, right? If I go 2 inches wider, I'm more than double the amount of weight that it can carry, right? It can carry 300 pounds at 1.5 inches. It can carry 700 pounds at 3.5 inches. And again, it's directly proportional. And so you have to make sure you remember which one is directly proportional, right? When the one following the term directly proportional is the x spot. The one before the term directly proportional is in the y spot. So y is directly proportional to x, and it's always written in this form. And then they'll give you a piece of information in order to solve for the k. Once I have the k, you have the simple equation where it's k times x equals y, and then they usually ask you to use it. Right? And just make sure you're careful. Are they asking me for x or y, and which value do they give me? They give me x or they give me y. And that finishes up 2.4. We only have one more chapter left to go, so hopefully you're starting to prepare for the quiz, the test. One more chapter to go.